will be talking about dipole interactions as well as electronegativity in this video. A dipole-dipole interaction is a type of intermolecular force that can only occur between polar molecules. Polar molecules will have a more negatively charged side and a more positively charged side. Because opposites attract, the more negatively charged side from one molecule will be attracted to the more positively charged side from another molecule, and vice versa. In this image here, we see an example of a dipole-dipole interaction. The molecule we're looking at is HCl, which is hydrochloric acid. I'll explain why shortly, but HCl is polar, with hydrogen being more positively charged and chlorine being more negatively charged. The positively charged hydrogen will then be attracted to a negatively charged chlorine from another molecule, which I represented by this line over here. This should sound familiar if you have watched the first video. This specific dotted line represents an intermolecular force, and more specifically, a dipole-dipole interaction. Remember, this does not represent an intermolecular force, and therefore is not a dipole-dipole interaction. You may be wondering, what is the difference between dipole-dipole interactions and a London dispersion force? To the right is a representation of a London dispersion force, and to the left is a representation of a dipole-dipole force. Well, London dispersion forces can occur between nonpolar molecules unlike dipole-dipole forces. London dispersion forces also rely on the movement of electrons, and because electrons are always moving, London dispersion forces are instantaneous. It is important to understand that polar molecules have London dispersion forces too, since they still are molecules with electron movement. So, to recap, London dispersion forces occur on all molecules, whether they are nonpolar or polar, but dipole-dipole interactions only occur with polar molecules. Earlier, I said that I'll explain why the hydrogen in HCl is positively charged and why the chlorine is negatively charged. The reason for that is something called electronegativity. Let's pretend that strong atoms get electrons. I will give a more technical definition at the end of the video, but for now, let's say that electronegativity is how strong an atom is. Chlorine has an electronegativity value of 3.2, while hydrogen has one of about 2.2. Don't worry too much about the numbers, all you need to know is that chlorine has a higher electronegativity than hydrogen, meaning that it is stronger than hydrogen. Remember that atoms share electrons in covalent bonds. However, that sharing is not equal. Chlorine is stronger than hydrogen, and because strong atoms get electrons, chlorine can hog that electron away from hydrogen. Since an electron carries a negative charge, this makes chlorine slightly more negatively charged than hydrogen when it is in an HCl molecule. Now, something important to keep in mind is that chlorine does not have a completely negative charge. It only has a slight negative charge, since chlorine is not strong enough to completely steal the electron from hydrogen. I'll represent this slight charge by drawing a small plus sign for hydrogen and a small minus sign for chlorine. Electronegativity is what's responsible for making some molecules polar. Now let's look at a case where the strengths have a bigger difference in something like NaCl. Sodium has an electronegativity value of only 0.93. It is very weak, and I show that by drawing it as a very small person. In this case, chlorine practically steals the electron from sodium since chlorine is so much stronger. We didn't see this happen with HCl since hydrogen was strong enough to the point where the electron could still be shared between hydrogen and chlorine. In this case, sodium is not strong enough to share the electron and chlorine ends up stealing it. This means that chlorine basically has a -1 charge, which gives sodium a +1 charge, which I will represent by drawing big charges. A large difference in electronegativity means that one atom is much stronger than the other, and there will likely be a full -1 and a full +1 charge. The electronegativity difference between hydrogen and chlorine is not as strong as the one between sodium and chlorine. For this reason, HCl contains a covalent bond, meaning the electron is still shared, just that chlorine has it most of the time, while NaCl contains an ionic bond, meaning the electron is not shared, since chlorine has it for 100% of the time. This chart here shows you an estimate of when certain bonds are considered covalent or ionic. Since the electronegativity difference of sodium and chlorine is greater than 1.8, it falls into the ionic category. On the other hand, the electronegativity difference of hydrogen and chlorine is between 0.4 to 1.8, so its bonds fall into the polar covalent category. To clarify, the bond between HCl and NaCl are not the same because HCl is covalent while NaCl is ionic. Now you may be wondering, how will I know what an atom's electronegativity is, or is there a trend to electronegativity? Yes, there is a trend. Electronegativity values are highest with fluorine. Generally speaking, the further away the atom is from fluorine, the lower its electronegativity value. The most notable exception is hydrogen. You might notice that the atoms here have the higher electronegativity values, while the atoms here have the lowest. The reason for this is valence electrons. Atoms are most stable if they have a full octet, which means 8 valence electrons. These atoms have only 1 valence electron, so their electronegativity is low because they would rather lose 1 electron to have a full shell instead of gaining 7 electrons. On the other hand, these atoms have 7 valence electrons, so their electronegativity value is high because they would rather gain 1 electron to have a full shell instead of losing 7 electrons. Now, we're going to talk about one more kind of intermolecular attraction. This is a special type of dipole-dipole interaction that results from a moderate difference in electronegativity. It only occurs in these following bonds. The electronegativity differences of these atoms are significant enough to be considered stronger than the typical dipole-dipole interactions in covalent molecules. As a result, they get their own category, called hydrogen bonds. Again, a hydrogen bond can only occur in a molecule with any of these bonds. Take a look at this molecule. Do you think it is capable of hydrogen bonding? Even though this molecule has both oxygen and hydrogen in it, the hydrogen is not bonded to the oxygen. It is instead bonded to the carbon. The electronegativity difference between oxygen and carbon is not significant enough for hydrogen bonding. Now, let's take a look at this molecule. This molecule has an oxygen-hydrogen bond over here. This fits the criteria in the above list right here. Therefore, this molecule is capable of hydrogen bonding. So the bottom line is to watch out. Molecules may have hydrogen in them as well as nitrogen, fluorine, or oxygen, but if that hydrogen is not bonded to either of those elements, the molecule cannot make a hydrogen bond, which is what we saw over here. I hope that's helpful. My more technical definition for electronegativity is up here. Anyways, as always, if you have any feedback or questions, leave them in the comments, and goodbye.